Good afternoon. In the last lecture, we talked about security assertions and how do we generate our security assertions. Now, I am going to talk about how do we apply those security assertions in specific scenarios, and I just decided to choose 4 scenarios just to show how do we apply those security assertions. Now, where does these scenarios come from? If you are a security verification engineer, scenarios comes from your threat model. What are the threats you are thinking? If it is a system on chip, then what are the things you are worried about? And this list comes from, if you recall, common weakness enumeration, common vulnerabilities enumeration. So, that database, these are the typical vulnerabilities, and the list of 4 I am showing, it is one of those 4 out of these 7. And if you recall, some of the vulnerabilities may not be unique, it may be a combination of the vulnerabilities. For example, an attacker might be able to try information leakage using malicious implants. So, for example, if you think of this circuitry, there is a hardware Trojan and this is the trigger corresponding to it, and the job of the trigger is basically to make sure some assets, this could be the key, birth date or anything that you do not want it to propagate to a primary output or an observable point, you do not want it to operate, and there might be if statement that stops it. That if statement might be saying if you are a privileged user, then something is supposed to propagate. In a normal execution mode, the privileged user is supposed to be 0, that variable, but what Trojan does, whenever you as an attacker want it, it will make that one 1, although you are in user mode, but that variable would be flipped to 1. It could be done through Trojan, or as you have seen when I talked about laser fault injection attack, it could be done through that, but no matter what it is, 2 attacks collectively will allow this information to leak from the point of assets to the payload. Now, for malicious implants, we have a day dedicated for it, but if you recall, the threat model for the malicious implant is the attacker is going to hide it in a place that is difficult to detect. For example, instead of putting on the top of the table, maybe it is going to put on the bottom where the visibility is less, people are less likely to bend and look. So, then if that is my threat model, then rare variables or rare signals is what we should be looking for. For example, in this definition, if we say a particular variable signal S becomes 0 with 99% of the time and it becomes 1 only 1% of the time, then that signal is rare for value 1. So, therefore, if we analyze the design and find, let us say in a design we have 3 rare signal A, B and C out of millions of signal. Depending on how many signal rare, what is your threshold, what is this cutoff, is it 1%, 0.1%, 5%. Once you change the threshold, number of variable will become rare, that set will increase. Once we have that set, now the assertion, even if you write manually, assertion would be, there are different types of assertions possible, because you do not know whether each attacker is going to create a trigger of only 1 signal, 2 signal, 3 signal. So, then you have to consider all possible combinations. So, if I have 3 rare signal, so here are the 3 assertions. If I consider a combination A, B, B, C, C, A, here are the 3 possible combinations. If I consider all of them A, B and C, here is the combination. Clearly, unless you put a really high threshold, number of signals too much, it is going to be exponential number of assertions. So, there is another level of elimination you have to do, but nonetheless what I wanted to demonstrate you, the automated system that generates it, this is the principle or philosophy it applies to it. What is the threat model, and based on the threat model, what are the possible assertions and generating those assertions. Now, of course, there are many techniques, I will talk 1 or 2 of them. How do we reduce the set, yet you get some level of guarantee? You are willing to sacrifice your exponential least, exponential in terms of number of rare signal, and yet you want to maintain certain level of vulnerability coverage. The way we talk about functional coverage, here we talk about vulnerability coverage. Any questions on how do we apply security assertions or how do you generate?
One question was there, like this is a rare signal, so we have put an assertion based on rare signals, but what if the rare signal is genuine? It's rare, but it is rare.
Interesting question. So, the question is, we are assuming the attacker is going to hide or create a trigger consisting of rare signal. Therefore, if that combination is true, then we are basically trying to make the assertion fail and stopping the program. So, the question is, what if the exact thing we are thinking that A and B or not A and B, that scenario or that gate AND gate is actually part of the original logic functionality. What do we do about it? So, the thing is that story is going to happen. Even rare signals are still the signals in the design, and even if it is 1%, it is still going to happen at some point in time. With low probability, even if you simulate, the chances of it happening or failing is low, and bigger the trigger is, chances of that happening, unless you are running millions and millions and millions of test cases and billions of clock cycle, even if it is part of the original functionality, it will not even happen. Only time it will happen if the attacker is trying to change the input, because what is attacker's objective? Whenever it wants to mount the attack, it will give the primary input in such a way, so that this trigger condition becomes true. So, that way we are kind of, it is true, it is going to be a lot of false negatives, but the thing is the odds of that happening in normal execution is low, but would such gates exist in normal logic? Yes. So, now let us look at illegal states and transition. So, some of this we talked about in the context of laser fault injection attack in the morning, and the idea is when you have a lot of states, they may be connected, some of them may not be connected, like some of the unspecified state. Where does this come from? Let us say you wrote a if then else statement or a case statement where you talked about 3 scenarios. In your mind you are thinking the finite state machine will have 3 states, but in reality if you synthesize using any synthesis tool, for example, Synopsys design compiler, whether it does one hot encoding or binary encoding, it is going to create 4 states. You did not design it, you may not pay attention, you may not test, but that state will be created. It will not look like this. Recall the register it will create with 2 bits. So, it has a probability of those 2 bits becoming corresponding to this variable 1 1 at some point, right. And some of these states you can designate as unauthorized state, authorized state, protected states. In layman terms, think about the password check we worked on the doorknob. Think of this one, somebody is trying to enter the password, this is checking the password, this is opening the door lock. So, then key idea is that we are trying to do that, we are trying to create assertion of. So, we do not want such a transition to happen from an unauthorized state directly to the protected state, like door opening without going through the password check. We do not want that to happen, and that you can similarly we do not want anything unspecified functionality, although I have drawn this link, but technically speaking this should not have any transition to any of the states, but this is the most dangerous. From nowhere it should not be opening the door, and you can write a property as simple as by the state's name implies if you are in S1 you should never go to S3, no matter how it is. Although I show a transition like this in the diagram S1 to S3, it could have been via something or some other mechanism, but such a transition should not happen. Any questions on illegal states and transitions? Remember, when state machines are this simple, you might be able to write by hand, it is possible, but when you have a complex state machines, lot of parallel concurrent finite state machines running in parallel, doing analyzing manually, figuring it out, is kind of impossible. That is where you kind of need automation and understand that basically whether it is a unauthorized state to protected state or unspecified state to protected state, all of those assertions need to be generated automatically. Now, in terms of information leakage, this is kind of involved. I will try to do as easy I can. So, tomorrow you guys are going to play colors, right. So, let us assume each of you decided to use only one color, one unique color, and your hand is full of that color. Now, whoever you apply the color, subsequently if we take any person at the end of the day, look at the number of colors in his or her body, then I will be able to figure out who are the people this person came in contact with. Now, this is not any unique idea, even in COVID days the contact tracing, that is how it worked. If you got COVID, the scary days of COVID, then where did you visit, then all of the people you visited or that vicinity, we kind of assume those people are also contact tracing individual, then we translating where did they go, it is the same analogy. And why are you talking about this analogy? Because I know there are certain variable like S, or certain variable like S is a secure asset, think of a key in the program. I do not want that variable to mingle with other variable such that somebody observing the primary output get a smell of that variable. I do not want that from a security expertise point of view, but the way you return program, this variable would be used in different places, in the part of the if statement, on the right hand side of somebody, on the left hand side of somebody, and that is the mingling story, right. So, here you see the S is on the right hand side and left hand side is A. That means A is getting information from S. If S is a secure asset, now A suddenly become, we call it contamination, it gets contaminated. If anybody get a smell of A or get the color of A, it gets the information about S. And this is a very trivial way of showing through if statement, for loop. There are many complicated relationship. Question is, how do we know? The way it works, there are many other ways of figuring out. The information flow tracking mechanism basically says as many variables as you have, you create those many tag variable. Like for S we created S underscore T, for B we created B underscore T. Anytime there is an assignment A equal to S, we create another assignment A underscore T equal to S underscore T, and this story continues for every assignment, for loop, if statement. There are ways of doing it, and then what you want to do, after we instrument with tags, we really want to check if B is the prime output variable, we want to check that S implies T, tag variable of S implies it is not tag variable of B. If their tag matches, their color matches, that means B, which is a primary output, anybody can see it, it will get information about S. That means there was a path. This basically means if this property ever fails, if this property fails, that means there was a path from S to B. If I draw it pictorially, let us say this is a design and S is somewhere and B is primary output, that means there is a complicated path, no matter mingling, eventually this value can propagate. That is the information leakage story. Now, in reality things are a lot more complicated, many times we may not be able to do it, because remember this is through simulation, and simulation means there is no guarantee, because AST and all this stuff or this assertion failure will happen only if you activated all of the paths. This could be a if statement, this could be inside for loop, another if statement. The probability of each if could be very low, and if you multiply those probability of this path happening during simulation is extremely low. And if you did not run enough test cases, in reality there is a leaky path, but this did not fail, falsely you will assume, well, this design do not have any leakage problem, but that is not true. So, that is why if there are formal guarantees that this property itself or assertion itself, you can call it as a property and you can do model check on it. Exactly this one, you can do model checking on this property, that in the eternity of this design execution, S underscore t will never imply always, it would imply such as always S underscore t implies not B underscore t. You can check all of that stuff. In this domain people also do static analysis, but that is not under purview of this. The way they do static analysis something like this: if AND gate has one of the input variable which is secure, the probability of this propagating here is 25%, because of 1 1 makes 1, all 0 0. So, you can compute the probability of this propagating to the output and you continue that at the gate level. In the RTL level or in the program level, if you have if statement, you compute those probabilities and compute how it flows. So, if you have 2 or 3 layer, probability is already very low, it may not seem much, then how is it useful? The way compiler gives you lots of warning or error, this tool will give you lot of list of leaky path with the probability number. Designer will go by the highest probability and slowly go one by one to figure out which one should I fix first, or do I fix, or is it it's a reasonable path, there is nothing to fix about. So, again the key idea is I wanted to explain that information leakage is a serious problem. I explained a method of using tag, this is called information flow tracking. Using tag, how would you instrument the design, and if you do instrument, then you can put an property like this. So, then your assertion generation problem is not just generating assertion, you also have to instrument the design, otherwise assertion generation would be useless. Any questions? Permissions and privileges is actually similar, I am going to skip, I have used the same finite state machine. So, that basically we are just saying it is not that S2 cannot go to S3, it is basically it has to be also a super user or whatever it is. So, some of the properties kind of look similar, but it basically this property is, are you authorized to go to that state, it is not saying do not go to that state. Here are some results, but simply if you are working in this area and you want to do the security assertion, your objective is to what is the minimum number of assertions I can generate to give the full coverage, whatever your threat model talks about it. And of course, you have to consider how much of time it would take and memory requirement to kind of for you to run those assertions. So, before I kind of conclude this kind of discussion, one thing I want to talk about, there are also static analysis tool which would do this on your behalf. So, similar to the assertion generation I talked about, there are many tools. One of the early ones is Goldmine, then there is Harm, and there are many of them. They automatically analyze the design and it will generate assertions for you, right. That may not be the exact security assertions you are looking for, but that would create certain variables and generate. This is another static analysis tool. It may not just on the surface, it may not look like these are security assertions, but if you look closely, buffer overflow is one of the common weaknesses. So, if you can get rid of buffer overflow issues from your design, then you are on a good area. Same thing about null pointer, valid pointer, memory allocation and all that arithmetic, undefined shift. You see the word undefined, that is kind of attacker's paradise, undefined, unspecified. So, there are tools that can do analyze your thing. So, this particular one is from trusted execution environment, security enclave, if you recall security kernel, the mechanism that allows us to do HTTPS and all that comfortably. Even all their application specific interface, those API functions, if we just run the open source static analysis, this is called linting tools, you can see the basically there are so many violations. There are so many violations of all that kind. That does not mean actually that API is buggy, that only means that has so many vulnerabilities. Security enclaves which supposed to give you protection, think of your bodyguard, the bodyguard's body itself needs medical attention. so much health issues with any of these function calls. So, to conclude the discussion of basically this issue is that simulation based validation, security validation is applicable for large design, but you cannot guarantee completeness. Formal methods gives mathematical proof, but you can apply only small and critical component, and assertion based validation is widely used for security verification for hardware, software as well as firmware design, all of them and actually together. So, what I am going to discuss now is basically how do we generate test to activate these assertion, as well as how do you refine some of these assertions. So, in the previous lecture we primarily talked about generation of assertions, but now we are going to talk about we will briefly touch upon that assertion generation just to recap, but we will primarily focus on how do we activate these security assertions, so that we know they are valid, and what is the scope or opportunity or challenges of doing dynamic refinement of those assertions. So, as we discussed earlier, all the security assertion story starts with the threat model. What are my vulnerabilities for which I have to generate the assertions, and there are a lot of automatic assertion generation method, such as some of the early ones or popular ones are gold mine. I will briefly talk about their basic philosophy, and all of these you can download and run. They are very stable, although it is academic tools, but they are very stable. The basic philosophy is that you run it, you have a design, hardware, software, it really does not matter, you have a design, you basically simulate it. You simulate and run, you can run with random tests and there could be efficient tests, but you run, and whatever traces it produce, the tool tries to figure out are there any invariants. For example, when things are getting generated, let us say you are building a truth table A, B and all that, and it is observing is it possible whenever A is 0, B is 0, is it possible when A is 1, B is 1 and so on and so forth. After observing, it is trying to figure out an invariant that A implies B, that whatever the value is A at specific clock cycle time, B also have the same behavior. It is trying to figure that out, instead of a designer saying it, instead of somebody analyzing the circuit figuring out, based on the simulation traces, it is trying to figure that out. Now, as you realize, maybe the up to the time it ran, that relationship exists. Now, this is a simple relationship I talked about, it could be really complicated relationship, big equation. Is it possible that if you run 10 minutes more, this relationship will fail? That is possible. That is why once these tools figure out this kind of invariant relationship, then they do model checking, and to check if that is that true for eternity, and then that becomes an assertion. So, this is the kind of story of generating functional assertions, and but these functional assertions are not kind of useful for monitoring security vulnerabilities. Can you tell me why? Because functional assertion checks for expected behaviors. Security vulnerabilities is exactly inverse of that, unexpected scenarios, exceptional scenarios that people typically do not specify. That is not completely true, because if you think about an addition, what will happen in an overflow, any architecture document clearly specifies that. So, in general I cannot make that statement, but most of the time people talk about what is the expected behavior of this design, and that is why it should not be surprised that for different design, if you kind of just use assertion. So, you insert some vulnerabilities, that is what we did, we inserted some vulnerabilities, we generated assertion using goldmine, lots of them, and we ran them just to see how many of them are covered. So, there are two approaches. One approach is what I talked earlier, specifically for scenarios like permissions, privileges and so on and so forth, you generate assertion to monitor security vulnerabilities, versus you generate generic assertions, functional assertions, and you hope those vulnerabilities will be captured. and for certain small designs that might be the case. Few designs, as you go bigger and bigger, remember AES is not a big design at all. Even for designs such as AES, it will not be able to cover anything. Now, so this is the overall view I talked about. Just to summarize, once you know the threat model, you kind of do the vulnerability analysis, you generate assertion, and then that assertions you put it in your design and you verify, simulate and all that, and you have two scenarios at that point. Either the assertion failed, it is a problem with the design, you fix the design, or the assertion itself is a problem. So, for example, in the assertion, when you put inside A and B, maybe this expression you wrote it wrong, it should have been not A and B. The understanding itself was wrong while you were writing the expression. So, then that need to be fixed. We already talked about the sample examples of, I am going to skip all of that. So, the question is now that we have all these assertions, how do we activate them? How do we check those assertions are valid? How do you guarantee when actual problem will happen, this assertion will actually fire for right reasons, not for wrong reasons? So, to understand that, we need to understand that we are talking about test generation. So, what is a test generation problem? It is an algorithm, you can do it manually, that would produce something. In case of processor validation, you need to produce some assembly instruction that you can run on your design, and it is supposed to produce some result, and you can check with the expected result. In this context, most of the companies, what they do is some form of constrained random test. So, random would be random, as the name suggests, you keep on applying some inputs. Constrained random is you kind of know where you are, what you want to achieve. So, for example, you know, if you have lots of branches or if statement, you kind of say, well, I covered 80% of the branches, but the 20% of the branches that you did not cover, you can keep running more and more tests. So, this is basically number of tests, this is number of tests, and this is basically branch coverage. Let us say branch coverage is our criteria. But normally if the branches have rare condition, the condition itself is extremely rare, you can keep running, it is not going to go up too far. So, that is why what company do, whatever they can achieve by random, constraint random, remaining they try to cover through various other mechanism. It may sound funny, they actually use some of the manufacturing tests also, just to increase the coverage. Then people would add some directed tests, some ATPG tests. Direct test people would write manually. If I know which branch I need to cover, they try to figure out what do I have to make the initial condition for this branch to be activated, right. So, if I want to do, so this, let us say this is the initial state, this is one of the branch that is not covered, and you keep on running a lot of tests, it may not activate, or you can just manually write one of the tests that would take you right there. Only problem is for small programs you can look at, okay, this is the if statement, I need to do a greater than 5, if I want to make a 6, what do I have to make to the previous assignment, what do I have to make to the for loop, you can keep going back and manually write. But when you have millions of instructions, this is not going to work, millions of lines of code, this is not going to work. So, then you can do, you can kind of use kind of automated method and to generate, but the problem with the automated method is, remember the automated method whatever you are trying to do manually, it would still try to do the same. But while it is trying to do, if the if statement has a rare condition, then you have to make the rare condition true. For you to activate this assertion, it has to make the rare condition true, and it is just not the rare condition true, you also have to make P as true. Remember, this P could be a complex expression, it may not be one variable, and you have to make P true and then Q as false in the next cycle. If you remember, P implied Q in Boolean logic, P implied Q is equivalent to not P or Q. So, we cannot make it fail non-vacuously, sorry. So, this logic will fail if P is false, but P is false is not what we are trying to check here. We want P to be true and Q should be failed. So, then you really have to satisfy these as well as this, all three of them you have to satisfy, the tool has to satisfy, and it could be a deeply embedded logic somewhere, and which is kind of the hardness of the problem. There are a lot of test generation method, I just want to summarize so that you kind of see what we are going to apply here. Of course, manual test writing is still prevalent in DSP community, microcontroller community, which is the robot community. They do not believe in any of these, they still do manually, because most of the instructions are so complicated, most of the control conditions are so complex, they manually write their test case. Random test generation is very easy, you can so quickly you can generate the test, but total time, if you look at the total time, test generation time plus simulation time, that could be huge. If you just consider test generation time, generating one test will take you 1 second, you hit the button, it gives you a test, any number. Formal method, which I am going to show kind of in a moment, it is good, but because it uses a formal method as the back end, it is going to have state space explosion. Then I am going to talk about kind of a semi formal method. There are many semi formal methods, I am going to talk about one of them, concolic testing, which is basically a combination of formal and semi formal. So, before I go further, the idea of formal and semi formal, I can give you an analogy. So, let us say you go home today and you see you do not have the key. Now, first thing you are going to do, you are going to say, oh, I was last in the classroom when I had the key. You are going to take your bike or car and very quickly come here. The taking the bike or car and coming very quickly is the simulation. And then you come to this room and you look very carefully all over the place, that is formal analysis. And after you do not find it, you said, oh no, not here, in the lunch time I think I had the key. Again from here you are going to very quickly go to the lunch place, that is again this going to the lunch place is again simulation, and then once you go to the lunch place where you had your lunch, you looking very carefully, that is basically formal. So, the idea of concolic testing is formal simulation, it is kind of in a loop of that in some manner, that is basically concolic. I will zoom into it, but is the key difference about these 4 major categories clear, and we are going to apply one of them, concolic, for activating assertions. So, let us first talk about how formal methods helps in this. So, let us think that your security condition that you are trying to satisfy, your assertion says decode equal to stalled. So, your assertion was assert decode unit dot stall, that was your assertion condition. What we are trying to do, we are trying to create a test case. If we run that test case, this statement should fail. So, that means if you want to do formal method, you give the decode stall not equal, you write the negation of it, give your design, give the negation of it, give it to a model checker. You know what model checker does, either it says you are satisfied or it finds a counter example, and this counter example is nothing but a read after write hazard in an architectural sense, and that is the instruction sequence, and that is your test, and that test is guaranteed to activate this assertion. Only problem with this, so basically you get a test by model checking design and not property. Whatever vulnerability you are going to or assertion condition, you do a negation of it, you get the test. Only problem is because it is using model checker, whether you do use model checker based on binary decision diagram we talked in the morning, or bounded model checking based on satisfiability, all can lead to state space explosion when your design is complex or property is complex or their intersection itself is complex enough, which pretty much true for any large design. So, therefore, it is very difficult to use them. There are a lot of research, how do we control this state space complexity. I am going to briefly touch upon them just to kind of show you what people have done over the years but then we move to concolic testing, which is what people are using today as we speak. So, what kind of stuff? So, this is basically an observation from Strichman. Strichman said that if you are solving or trying to find if there is a problem with somebody in your design in one cycle, and you figured out certain behavior, if you think this as a tree, you figured out that solution does not exist in the left subtree. If this is a tree, that observation will hold even if you unroll the design for 2 clock cycles. So, if you want to take analogy of a program, if for loop you are doing iterations, if the first iteration something did not happen, you are trying to see if anything happens second iteration, any observation, any understanding, any insight you got from the first iteration, that still hold in the second iteration. So, do not in the second iteration your tree would be much bigger, but it is the observation that the solution cannot exist in the left subtree, in SAT term that is called conflict clause, or so that situation still holds, and that is what it says. If the same property across bound or the size, or think about traffic light controller, car is waiting for 1 second, 2 second, 5 second, if something did not hold true for 1 second, it is not going to hold for 2 seconds, 5 seconds. So, then your search space, although exponentially it increases as you keep unrolling, but certain portions you can mark it black, you do not have to search. So, that is basically what Strichman has showed. Then there are many other works where different research group, including our group, we looked at. First of all, we are not trying to solve one assertion in a design. If design have millions of lines of code, it is going to have thousands or millions of assertions. We are trying to find tests for all of those assertions, not just one of them. And if those assertions have some commonality, so let us say you have an assert A and B, maybe another assert A and B and C, or A and B or C. You can have many properties, they might have overlap not by looking at the property, that would be misleading. The overlap is, if this is your design, if you consider the property, the kind of slice it cuts on the design, let us say A is one of the output. If you are trying to say something about A, then only thing relevant is from that output to all these inputs. These inputs are not relevant, this logic is not relevant, that is basically slicing. You could manually slice the design and run model checker. Most of the model checker today will slice it for you, you do not have to do anything. Now, so this is a slice for this property P1 or this assertion A1. Then for P2 it might be doing another slice, I am just randomly, let me take a different color. So, let us say it might be making a slice of this. So, then any learning or understanding you got from this part, no matter which property you solve first, that learning you can forward to the next property. So, this basically utilization of learning in case of Strichman from one bound to the next bound, your first year of college to your next year of college, next phase of your life, from one property to another property. In fact, there are from one symmetry to another symmetry. When you have a multi-core architecture, for a classical example, if you are trying to solve that problem and based on that solution you figured out certain conditions should not hold, certain subtree is not relevant, you can solve the same thing for another core, or you do not have to solve for the other core, you can derive directly from the first core itself. If you do the job right, variable naming right, then you can solve for, if you have 32 core machine, you complexity reduce by 32, actually reduce more, because the complexity is actually 2 to the power 32. So, from 2 to the power 32 you reduce it to 2 to the power 1, and the solutions are still valid solutions. So, you can exploit symmetry across. Yes, please.
Previous slide. How do you transfer this property from one form to another?
Right. So, the way it works, so design and property or assertion that produces the conjunctive normal form, those clauses. So, design and P2 will produce corresponding conjunctive normal forms. So, the intersection of these two normal and then that is one thing. Second thing is we have some learning here, some learning L1, something we learned that go to left, do not go right, do not talk to strangers, whatever we learned, that learning I can forward to the project property 2 only if that learning is relevant in the intersection of these CNFs.
But what are learning for A? You don't need the entire thing for B. Right?
We should not use entire thing from B. We might have learned lot of stuff. We should not apply all of it. That is why we need to figure out the intersection and figure out which learnings are relevant for B. Otherwise, it actually will misguide the next property.
How do you find out which is relevant?
So, that is the point. Relevant is this cone of influence or cone of intersection. Now, if the variable we are dealing with whatever, if it is a C and that C is completely contained in the intersection, because then that learning is relevant. So, the complexity of this is basically intersection time of CNFs.
But you are talking about properties, right, not variables. So
Oh, the property imposes the slicing on the design, property imposes slicing on the design. Eventually, you are solving for those variables only. So, that is the graph. If you think of a graph level, if this subgraph is also, because design is same, that is the reason. If design also was different, then all of these are useless. Design remains the same, property is different, but in fact properties are also not drastically different. If variables are different, output everything is different, then overlap would be 0. If overlap is 0, there is no learning can be forwarded. So, I am going to, so basically any form of similarity can be exploited. In fact, if you think about it, when you are solving for multiple property for multiple core, you can forward learning from across the timescape, between the cores and between the properties. So, there is a lot of learning opportunity for reducing the time. But no matter what you do, problem with model checking or any of these approaches, any of the formal verification approaches, most of them, they give the guarantee on a abstracted model, formal model. So, if you think about it, if you are a theorem prover person or doing PhD with a theorem proving expert, most likely you are looking at a design on the left hand side of your monitor, on the right hand side of your monitor you are writing in some formal language. It could be SMV, it could be anything. There are some automated tool SMV or COQ, COC or any of those you are writing that. And let us say you guarantee something, what you guaranteed on that formal model, not actual model, and the actual VHDL Verilog design would be synthesized. So, it is kind of a serious problem. We can argue, well, actually the formal model was automatically generated from the Verilog or VHDL to the formal, but it still it is a translation. Anytime you do a translation or abstraction, it would lead to potential false positive or false negative. So, that problem can be solved. So, that is what I meant by there is a need to translate a translation to somewhere, that is error prone, and also model checker cannot handle what we really want something like this, which is the concolic testing. What we really want is, if I have a design, it does not matter what this design is doing, if I want to activate a specific statement, our assertion, if I want to activate a specific statement, then the way concolic works is, first of all we instrument this one, instrumentation is a linear time complexity. So, for every statement, think about it, for every statement that is there, instrumentation will insert a display command, I am here, I am here, I am here, exactly the way we debug, I am here 1, I am here 2, you manually know here 1 meaning I entered the first for loop, here 2 means I entered the second for loop, you instrument that. And if you instrument the design, you do not change the functionality, because those are display commands or printf commands. Once you have that, then you run any random test, does not matter what test it is, you run, it is going to produce something, those instrumented thing, where you are, where you have been, which branches you covered and so on and so forth. And then you kind of from that printout, you generate some constraints for a constraint solver format, and then you try to figure out, did I activate that particular display line, and if the answer is I did not, then you repeat this process. If answer is yep, whatever you printed, remember when you run, if I have, let us say, a simple sequential statement easy to visualize, you have a if part, you have a else part, and when you simulate, let us say that that is all you have, if part and else part. When you simulate, you have only two choices, either simulation gone through this path or simulation gone through that path, that is it. No concurrency, no if statement inside if statement. So, the random test you run, let us say this is what you wanted to activate, something here. The simulation you did, if it has gone through this path, then clearly that printout will say nope, I did not get it. Then next time you simulate, you have to modify your test case now. You cannot run the same test case, because if you run the same test case, it is going to execute through the same path. If you have multiple if statement, it is going to go through same if path or else path, same chain or trace it will go through. Next time when I go through, I have only one choice in this example. Last time I need to flip this branch instead of going this. So, to flip this, I have to change to my test. This system will do that, this system of equation will flip. So, next time you simulate, it will go through the other path, and in this example you are guaranteed to activate that scenario. So, let me but the thing I want you to understand is that concolic testing is designed to do branch coverage, that is all it can do, which other branches can be covered. If I want to do assertion coverage, I have to convert these assertions and branches. It just so happen assertions are branches. If you think of assert request equal to acknowledge, it is basically if request to not equal to this, then $display assertion activated. You can always convert any assertion statement into branches, whether it is an immediate assertion which is embedded inside a sequential area, or concurrent assertion which is kind of inside always. So, then you convert that one as always, if something then something and so on and so forth, you can always create a conversion automatically like that. So, basically once you construct a branch, then I can run concolic testing and ask concolic testing to cover specific branches. And the way concolic testing works, let me see if I can do the animation. So, this is your design. By the way, concolic testing also works on software design. In fact, it coincidentally concolic testing started in software community. I borrowed it from software community and applied it to hardware community in early 2015, 2012. So, now it is used in both communities. So, but it came from Kaushik Sen from UC Berkeley, this idea of concolic, and the name came from the fact concrete and symbolic, the CON from concrete and the last part leak of symbolic. So, that is so concrete is the simulation, symbolic is the formal analysis, and you will see all of that now. So, basically you simulate first with the random value, and it just so happen, let us say random computation gone through this path. It took the if of all of the branches on the left, and all of these are if statements, and my target is right here. That is the statement, is the assertion statement I am trying to activate and find a test for. Anybody remember why do I want to activate the assertion? Why do I care? I generated the assertion, I put it in the design, if anything happens assertion will fail and I will know. Why do I want to generate the test and going through all these pain?
To verify that assertion.
Go ahead, ma'am.
Because of the assertion also be false.
Assertion condition I might not have written correctly, so it can fail in a wrong time. So, I want to make sure the assertion I wrote, when it is supposed to fail, it fails correctly, it is a valid assertion. So, during design time itself I have to generate a test, check my assertion, so that run time there is no more false positive, false negative story. Thank you. So, now this is the path constraint, and then did it cover, I checked whether it covered, that is through symbolic analysis. If answer is no, I have three choices, this one or this one. There are many heuristics we developed over the years, different research group developed, and of course, this would have been nice, because manually visually you can see it, but in real life that does not happen. You might be thinking why not, if it is a control flow graph, if you compute a distance from the target, if I keep numbering, right, this is 0, this it happens to be same color, 1 second, this is 0, this is distance 1, this is distance 2, this is distance 3, this is 4, this is 5. If I compute distances 2, 3, 4, 5, 6, 7, 8, oh 8 sorry I was doing wrong. If this is 0, this is 1, this should also be 2, distance of 2. But anyway, so if I know where I want to go, I need to flip the branch which has the shortest distance from that. So, ideally I should do that. This idea works if you can completely unroll the control flow graph CDFG. Unfortunately, we cannot do that, because in a software design it is still easy. Hardware design, you have multiple parallel control flow graph there, and this target, it may look like this, but this target may not be activable in 2 cycles. It may be, let us think about it, if you write something in the memory, 20 cycles later if you read from memory, so there is a sequence of dependency. So, there is a 50 cycle 60 cycle dependency. Unless you unroll for 60 cycles, then do this kind of marking, then you know which branch is closer and which branch is far. The near and far otherwise is not obvious, but either way in this example the system will flip, sorry let me do the animation again, system will flip that, and now when it flips, the original test case gets slightly modified just to make sure next time we simulate this branch would be included, everything else is not guaranteed. And let us say you simulate, that path got active, that path got simulated, and then our target is still not in that path, and again this time we are trying to do flip this particular branch, and then finally it will cover. So, really the key problem in concolic testing is which branch to flip. So, first problem was any security assertion we have to convert into branch coverage problem, and then second thing is once you convert to branch coverage problem, next aspect is how do you from that branch coverage problem, how do you get to which branches to flip to get to the target as quickly as possible. So, here is another animation just to show the first one, when you generate input, it basically took through a path, and then you want to flip let us say this particular branch, then alternate path you have to solve symbolically what modification of your original test case will make you flip that path, and you keep doing that until you reach the target. So, basically I just summarize it here. When you have a design and the security assertion, you need design instrumentation which will print which path the simulation has took. Then you kind of do simulation, and simulation trace constraint generation, you kind of do constraint solving. This is the formal part, simulation is the simulation part, this is the concrete and this is the symbolic, and then you basically get a test. Let us say your original test was a equal to 1, a is a primary input, then constraint solver said nope, it needs to be 0. Of course, this case it is a 2 choice, it is done, but normally it could be complicated lot of inputs, or a may not be a Boolean variable, it may be non Boolean, and eventually you get the test to activate that. It is just that it is doing it automatically. Now, normally most of the time people ask me this question that, let me just talk about it. So, scalability wise, so if you use any kind of existing model checker, one of the popular one is EBMC, then it is on, or versus you do the concolic. Concolic is lot more linear, and this is kind of exponential when you. So, this is the AES design unrolled for different kind of depth. Let me skip all of that. Okay. So, before I go for dynamic refinement, let me ask try to answer one of the question most people ask, which is if this is my search space, my target is farthest away from the where I started, maybe originally when you started, maybe this is how you are looking, then you are looking here, then you are looking there, then you are looking there. So, it is possible you have to cover the whole state space in the worst case to find the point. Then how is it concolic better than formal method which also tries to cover the whole state space? Would any of you attempt to answer that?
DFS method.
DFS method. Why DFS method is better than what formal?
Because it's go from starting with go from all the branches.
If you do not like DFS, we can do BFS, but the thing is, why is it DFS or a BFS, depth first search or breadth first search, better than doing formal analysis like what model checker does?
No idea.
So, the complex, it may look that way, but it is not true for two reasons. One is, formal method is trying to handle all of these millions or billions of states at the same time and then give up. If I put 100 or 200 kilograms on you, you may not be able to carry. But if I give you 10 kilogram at a time, sure, you have to make 20 trips, you still be able to do it. This is the same analogy. It is handling one tiny part at a time, and theoretically extreme case, it might have to go through the whole state space. It might take a long time, but it would still proceed. Formal will give up in the first few seconds, because it is trying to construct the whole design and unroll, and the memory in your computer, the size of the states machine would be larger than the memory in your device, and that is exactly basically state space explosion, but this will go slowly. That is one thing. Second thing is, in fact, in the worst case this will not happen. If your heuristics are right, then remember the branch flipping. Why would I be flipping this one, then this one, then this one? I should be flipping somewhere here and very quickly come closer to this and very quickly come closer to that, if we do it right. Of course, things are a little more complicated, that is one thing. Second thing is, the number of security assertions are in the order of thousands or millions, right. So, therefore, when on the way you are covering multiple targets. In fact, there are a lot of research in this domain. How do we cover multiple target? Should we treat them as independent targets? Should we apply concolic testing, or should we kind of rank order them and solve them knowing other ones you are solving? Think of the multiple property Strichman or other solutions in the normal model checking domain. Is this lot of such solutions exist. In software domain, people normally do uniform search. They basically start from left to right and as many of the targets as they can cover, and their case target is branches, as many branches as they can cover as they go sweep through. For our case, only difference is we are only interested in activating the security assertions, and we still want to cover as many of them as possible, as little time as possible. And even if we have to cover the whole state space in the story, we are doing one little chunk at a time. So, therefore, it is scalable. So, we stop for the break. Yes, please.
Sir, in the concolic one, sir, it seems that the branch flipping, the better the branch flipping, the better this will be.
Faster you will converge, yes.
So, and that would depend on the heuristic that I apply on.
That depends on the heuristics you apply.
So, sir, like some example of what are the kind of heuristics?
Okay, one example I already said. So, people use reinforcement learning, that I discussed on the first day. So, machine learning is used everywhere. So, one of the heuristic is, if this is target, you mark it as, let me do marking in a different color. If this is target, you mark it as 0 and this is 1. If this is 1, this is 2, this is 2, distance wise this is 2, and if this is 2, this is 3, if this is 3, this is 4, this is 4. So, depending on where you are, let us say you are in this particular path, when you are trying to see which one to flip, you do not want to flip 4, you do not want to flip 3, you of course want to flip 2. The number that is smallest there, but the reason that does not work, because unless you unroll it, for software domain it works like a charm, but in hardware domain, because you not only have this, you have another parallel one, maybe another parallel one. So, it is basically the global control flow graph is a intersection of all of them. Think of this is a state machine, this is a state machine, this is a state machine. It is basically cross product of all the state machines you have to consider, and you have to unroll it for millions of cycle until the target becomes activated. So, constructing that, if you try constructing that, then you will have the same problem as formal method. So, that is why it has to be a lazy construction. Do not construct something unless you have to. That is why these numbers is, I call it a heuristic, otherwise I will call it optimal, because if you are flipping this branch, what is the possibility that now we might say, under what circumstances do you have to flip this? Remember, I might have to flip this I might have to flip 3 to make certain conditions here, then something here will be activated. After that I have to flip this, then this branch will be activated, because think of memory read and write. Yes, this might be writing to memory. So, writing memory has to be activated, after that this reading component will get activated, and those are running in parallel. Those are parallel finite state machines.
So instead of so instead of deciding about the distance from the node, if we think about the distance in terms of property, right? So suppose I have say P1 and P2 and P3 condition, then it is happening, but your target is not P1, not P2 and not P3, right? So I mean, is there any some kind of way I can distance, I can identify the distance between two properties?
Right. So, in this particular discussion we are not talking about how do we make use of one property you already covered, how do we make use of, all we are saying we only have one target. This is where your assert statement is sitting, assert whatever that is. So, we are looking at it as a branch coverage and statement coverage problem. That is how concurrent testing looks at everything, unless somebody fundamentally changes the paradigm. So, basically concurrent testing is how do we cover different branches quickly, so that I can activate that statement wherever it is, and in a scalable manner, going one path at a time. So, so this is one of the heuristics. There are many. There are at least, I have seen at least 20-30 papers in software domain. Hardware domain there could be might be 2 or 3 papers. Many heuristics based on many other aspects of the design. We will visit in another 30 minutes. Thank you.